Hello everyone, my name is Prateek Arora and I'm a PhD student with the Robotic Workers Lab at the University of Nevada, Reno. Today I will present our work on mobile manipulation-based deployment of micro-aerial robot scouts through constricted aperture-like ingress points. This work is motivated by the wide range of significant mobility challenges found in real-world settings which are encountered during search and rescue and/or reconnaissance missions into disaster zones or other unknown environments. More specifically, the environment may contain highly confined spaces or constricted openings that lead to caved-in paths which are otherwise inaccessible. In extreme cases, such narrow entry barriers cannot be physically overcome by a single exploring agent. To this end, we propose that a heterogeneous system of systems robotic platform can gain entry into highly constricted spaces by autonomously detecting marginal ingress opportunity in the environment and deploy a different class of miniature robots through them by intelligently leveraging high-precision mobile manipulation. These may act as scouts and allow to resume the exploration and reconnaissance mission past the tight physical barrier. Our problem formulation comprises the following subproblems. Volumetric exploration. This is defined as a receding horizon-based execution of motion plans that aims to maximize the cumulative expected observations of unknown environments. In the proposed approach, it is assumed that this pipeline almost immediately reaches maximum possible exploration gain, and hence this problem is mentioned here for completeness. Constricted aperture MAV deployment. This refers to the ability to first detect ingress points in the environment that marginally fit the MAV, followed by hierarchical ranking of candidate aperture to select the most consistent detection that allows to reject spurious or inconsistent observations. Second, examine the candidate aperture profile from a closer vantage point to find the end effector poses that precisely deploy the MAV through it. And lastly, plan for a collision-free sequence of arm trajectories to slip the MAV past the aperture while properly positioning it to respect its takeoff safety constraints. Visually served exploration. This refers to the ability to navigate and explore without building a comprehensive map of the environment while relying on data of a simple imaging sensor. For our proposed approach, we assume that the robot is already performing a variant of next best view-based exploration planning autonomously, which almost immediately reaches the maximum possible exploration gain. The robot also relies on a mid-range traversability estimation and graph construction regarding the environment terrain based on our prior work referenced in the slide. In the beginning, the exploration mission is considered stuck. That is, there are no traversable routes that offer further exploration gain. Consequently, our pipeline is engaged. This starts by detecting caved-in hole-like apertures, followed by a closer profile analysis of the most consistent aperture, and finally, computing a feasible motion plan for the mobile manipulation system, the arm, and the MAV in order to deploy MAV for continued exploration into the blocked-off regions. For standard practice, we consider 3D volumetric map representation containing occupied, free, or unknown status voxels. We define the following. Aperture, a caved-in hole-like pocket, that is, planar subsets of the depth map ds depressed by at least a 3D depth threshold value dc, such that the contour Ca can be detected. Furthermore, the voxel inside Ca up to a depth threshold of dA belong to the free voxel subset. Launch pose. This is defined as the Euler angle parameterized reference pose for the MAV such that the translation part lies beyond the aperture and the orientation is bounded by roll and pitch constraints that allow safe takeoff. These constraints prevent the MAV from collision with the environment due to aggressive thrusting during takeoff. Our aperture detection pipeline relies on an n-frame sliding window dense point cloud data DNS comprising of all the incoming point cloud data within a window of size n, transformed and stacked per a common frame Fi to get a dense 3D representation of the local environment. Here, Fi is a frame instantaneously coincident with a sensor frame Fs and inertially aligned. We proceed to perform plane segmentation to extract a major model plane in the general form alpha x plus beta y plus gamma z equal to delta using ransack, including an additional constraint to restrain the maximum specified angular deviation of the plane normal from the depth aligned sensor frame axis, ensuring that the plane does not correspond to the ground plane. Subsequently, we extract a dense point cloud corresponding to the major model plane and transform it to the frontoparallel view of the sensor, essentially representing the plane perpendicular to the depth z-axis of the sensor frame. Following this, we obtain a floating point image representation by employing pinhole camera model-based projection, which significantly reduces the search space. Next, we perform morphological opening and canny edge detection on the binary version of floating point image, followed by contour detection to derive a set of candidate contours AS. At the same time, we compute 2D projection of the frontoparallel view of the MAV mesh and project it onto the model plane. From the contour set AS, we keep the contours that are A, hollow regions depressed beyond the model plane by at least a depth threshold of DC, B, marginally wide where the aperture contour area is larger than the MAV contour area. This pipeline continuously detects candidate apertures while the eye-in-hand sensor mounted on the manipulator arm performs a scanning motion of the MMS's environment. Sensor noise, discretization errors, and simplified metrics for accepting large enough contours naturally lead to false positive aperture detection. To filter out such spurious detections and allow hierarchical focus of the attention of the MMS, we operate by updating the probabilistic belief of each aperture centroid location detected. For each voxel MI in the sensor field of view, we update a log likelihood metric LA that corresponds to its probability to be a good aperture candidate that ultimately builds a confidence score of candidate aperture detections with increased consistency. This is equivalent to the hits or misses update model, where hits corresponds to an aperture detection and misses correspond to the remaining voxels inside the sensor's unobstructed field of view. This pipeline is used to perform collision-free navigation of the MMS near the most consistent aperture and position the manipulator arm such that the aperture lies within the eye-in-hand sensor's field of view. We begin by composing a set point pose PA corresponding to the most consistent aperture detection, followed by projecting a cone of constant radius of 2 meters onto the ground map. We randomly sample candidate poses for the mobile robot base and perform collision checking by the volumetric map M. For each surviving candidate base location BI, we proceed as follows. First, compute an end effector pose that maintains sight of the characterized aperture. Second, leveraging ground map connectivity graph based on our prior work, compute an admissible motion plan for the MMS that is collision-free and terrain traversability aware. And finally, employ inverse kinematic-based collision-aware motion planning to examine whether a feasible motion plan for the desired end effector pose exists. The pipeline is terminated as soon as a feasible solution is found and the MMS is commanded to navigate towards the goal. This part initiates as soon as the MMS reaches the goal and the aperture is in the field of view of the eye-in-hand mounted sensor. The previously described aperture detection pipeline is leveraged to detect the characterized aperture from a closer viewpoint now and to acquire a high-resolution aperture contour CA as well as a scaled MAV contour CM. We proceed to perform exhaustive search to compute a configuration of the MAV contour that fully lies in the interior of the aperture contour. Initially, we create a set G of all possible point pairs belonging to the aperture contour such that the Euclidean norm of the line Lx1x2 joining the points pair is greater in length than the major axis of MAV contour and that the line lies fully inside the aperture contour. We follow by ranking the elements of G according to the heuristic highlighted in the current slide. At this point, the set G contains point pairs xi(xj) such that the line Lxi(xj) is closer in length and orientation with respect to the major and minor axes of the aperture contour, lies in the interior of the aperture contour, and has Euclidean norm greater than the major axis of the MAV contour. We subsequently create an empty set V and proceed to evaluate contour intersection to acquire any collision-free MAV poses. For all the line segments joining the point pairs xi(xj) in the set G, we proceed as follows. We get the transformed MAV contour CTM such that the MAV contour is oriented along the line and its center of mass is positioned at the midpoint of the line. If the transformed contour and the aperture contour are immediately found to be non-intersecting, then append the configuration P theta to the set V. If the contours are intersecting, however, append them to an initially failed set F. If no valid configurations are found, we perform sliding search along the line segments in the initially failed set F, more specifically with the major axis of the MAV's contour initially oriented and aligned with the center of the aperture line Lxi(xj. We shift the CM 1 pixel unit to the left and then to the right interchangeably. We terminate the search along either side as soon as the edge of the transformed MAV contour coincides with the endpoint of the line. At the same time, we append any discovered configurations P' and theta which correspond to non-intersecting contours to the set V. The valid poses in the set V are transformed to corresponding 3D pre-launch poses expressed in the sensor frame of reference and forwarded to the ARM motion planning pipeline. It is highlighted here that ranking the aperture contour point-to-point lines Lx, Ixj by their proximity to the major and minor axis of the entire CA aperture contour is intended to provide an efficient solution for convex shapes. However, the exhaustive nature of the search can find solution for contour profiles with high degree of concavities. This pipeline pertains to the planning for manipulator arm trajectories which will deploy the MAV through the aperture and at an appropriate launch pose. For each pre-launch pose, we proceed as follows. With an initial set point G and the current arm configuration as a start state, we compute a motion plan that allows the MAV to be aligned with the aperture. Then, with G as the new start state and the pre-launch pose as the end effector goal state, we compute a motion plan that precisely slips the MAV through the aperture. The final motion planning step aims to orient the end effector at a pose that respects the takeoff constraints of the MAV. If all the three motion plans are successful, we plan to grasp the two MAVs located at known positions on board the body of MMS, starting from the same initial point G. Changing these motion plans together in appropriate order allows the execution of MAV deployment through the constricted aperture as laid out before. For the mapless exploration using the resource-constrained MAVs as a microscouts, we propose a pipeline that leverages a trained model for monocular depth estimation referenced in this slide. The network is deployed onboard the MMS's powerful GPU and is used to provide dense pixel-wise depth inference based on the monocular visual imagery that is wirelessly relayed by the MAV. We divide the resulting depth image into three-column subsets and follow up with simple pixel averaging, computing a 3x1 action vector. This corresponds to a control allocation strategy comprises of three actions, namely forward, clockwise yaw, and counterclockwise yaw, and aims to move and orient the MAV towards the region of greater depth. The corresponding command is relayed forward to the MAV, which resumes its navigation into the unexplored environment as instructed by the carrier MMS. We experimentally deployed and tested the proposed algorithms on an in-house developed autonomous mobile manipulation system, which is equipped with all the required perception, computation, and manipulation capabilities, as well as the capacity for autonomous real-time simultaneous localization and mapping, exploration and traversability aware path planning, as well as manipulation motion planning. The MMS performs a sweeping motion to detect aperture candidates and at the same time perform hierarchical ranking based on the probabilistic belief update strategy. The red plane corresponds to the Ransec model plane, while the colored spheres correspond to each candidate aperture detection. While there are false positive detections, most of the detections are near the prominent aperture, essentially building up the confidence of that particular opening as a good marginal ingress point. Finally, the most consistent aperture is extracted and the MMS is commanded to navigate near it while maintaining the sight of it. At this point, the aperture contour analysis pipeline is initiated and it performs close-up characterization of the aperture. Upon characterization and determination of feasible launch poses, the MMS proceeds to plan for arm trajectories to deploy the MAV robot through the aperture. After computing the motion plans, the robot reaches to grasp the first MAV, positions it in front of the aperture while aligning it to a pose that fits the aperture, followed by gently and precisely slipping it through, and finally orienting the end effector to respect takeoff constraints. It is noted that this last motion is mostly rotational in nature. After the sequence of trajectories are executed, the MAV is ready to take off based on an appropriately timed command. Immediately after takeoff, based on the depth dense estimates of the relayed visual imagery, the MMS guides the MAV towards the end of passageway while avoiding obstacles on either side according to the proposed visual surveying policy. At the passageway's end, the first MAV takes a right turn and continues down the long hallway. For the purposes of this experiment, we consider the scout mission terminated as soon as an object of interest is detected on the relayed image. The MMS issues a landing command and proceeds to deploy the second MAV, which also safely navigates down the passageway, turning left on the hallway, also discovering another object of interest before its mission is terminated. The detailed experimental sequence is provided as an accompanying video to our paper. Thank you for your attention. Please feel free to ask any questions or contact us directly for any further information.